Now we turn to the circular variant. This is a list with no end. The last node points back to the first, so the whole thing forms a ring. Let's build a ring. This function is ring insert end. A ring needs no head handle at all, because tail arrow next always names the first node. So we pass in the tail and we return the new tail. We call malloc to make a new node and store its address in X. If malloc fails, we return the tail we were given, so the ring is unchanged. Then we store the value in X arrow data. Now the base case, and we handle it first. If tail is null, the ring is empty, so X is the only node. We set X arrow next to X, and X arrow prev to X. The node points at itself both ways, and we return it. Keep that edge case in mind, because every ring operation has to cope with it. Now the ring already has nodes. First we read head, which is tail arrow next. Then we splice X in with 4 writes, and the order matters. Write 1, X arrow next becomes head, so the new node points forward at the first node. Write 2, X arrow prev becomes tail, so the new node points back at the old last node. The new nodes on 2 links are set first, exactly as before. Then the neighbors. Write 3, tail arrow next becomes X, so the old last node points forward at the new node. Write 4, head arrow prev becomes X, so the first node points back at the new node. The splice is complete, so X is the new tail, and we return X. The key idea here is simple. A ring of one node points at itself in both directions. That means X arrow next equals X, and X arrow prev equals X. This is the base case that every ring insert must handle. Now let's walk a ring and print every node. There is a catch. There is no null to test, because on a ring next never becomes null. So the stock condition is different. We stop when we are back at the node we started from. Here is that starting node, the one the start arrow points at. We walk forward from it, one node at a time, all the way around. Because the ring closes, we will come back to this same node. And that return is the only signal we get. So the loop body has to run at least once before the test makes any sense. Look at the code. The function takes the start node. If start is null, the ring is empty, so we return. Otherwise, we set cur to start. Then we use a do while loop. We run the body once first. We print cur arrow data, then we advance with cur becomes cur arrow next. Only after that do we test the condition, cur not equals start. When cur comes back to start, the loop stops. One trap to watch. You may want to reuse chapter 4's loop while cur not equal null, but on a ring, next is never null. That loop spins forever, so stop on cur not equal start instead. Let's predict first. Why is this written as a do while, and not a plain while that checks cur not equal start before the first print? Think about what cur equals when we enter the loop. The answer. On entry, cur equals start already. So a pre-checked while would see that they match and print nothing at all. The loop must run its body once before the have we returned test makes any sense. A ring has a real use in scheduling. This is a simplified round-robin model. A scheduler steps forward through a ring of processes. First, we guard the empty ring. If start is null, there is nothing to run, so we return. Otherwise, we set cur to start and we loop for a fixed number of steps. Each time we run the process at cur, then we advance with cur becomes cur arrow next. That step wraps forever because the ring has no end. So the number of steps, not the ring, is what stops the run. Let's trace 6 quanta over a ring of 4 processes. Quantum 1. We run P1 and cur moves to P2. Quantum 2. We run P2 and cur moves to P3. Quantum 3. We run P3 and cur moves to P4. Quantum 4. We run P4. Now cur wraps back to P1 because the ring has no end. This is the wraparound in action. Quantum 5. We run P1 a second time and cur moves to P2. Quantum 6. We run P2 a second time. The schedule keeps looping for as long as we ask. Let's look at the cost. Each step is big, O of 1, because it is just one next. There is no end of the ring case to handle. That is the payoff of closing the loop. And a quick note. This is a simplified model. A real scheduler like modern Linux keeps its runnable tasks in a red-black tree, not this ring. But circular lists are still used widely elsewhere in the kernel.